Happy Valentine's Day and welcome to the first exam review. So we're going to mainly just go through the 20 questions that I have in here. Remember that your actual exam will be 20 questions as well. A little bit about how it works, since this may be your first chemistry exam for a lot of you. So there is a test bank, a question bank of about 490 total questions, but they are grouped up into categories. So the topics that you see in this review, the distribution of topics, the number of questions in each topic is going to be roughly the same as what you'll see on your actual exam. Keep in mind there's a lot of variety in the types of questions we ask, so you're going to have to study a lot bigger and broader than just looking at these set of 20, but it'll give you an idea of what topics we're covering and what sort of ratio. And then the other thing to keep in mind is that for this exam review, obviously the main purpose of this is to help you guys out, so I do welcome you to stop me anytime if you have questions. Try to keep it somewhat relevant to the topic we're currently discussing, just so we can keep things as orderly as possible, but you don't necessarily only have to ask me about the specific problem that's on here. If there's anything related to that topic that you're unsure about and want me to rehash, I'll be happy to do that as well, so just interrupt me anytime. And then the other thing is that this year's review is only slightly different than last year's, but if I start doing the wrong problem at some point, just yell at me, because it might happen, but hopefully not. All right, so with that, we're going to get into the first question, which is, so it's asking about mass laws. Which mass law is demonstrated by the fact that sodium chloride mined in Goderich, Ontario, which is the largest salt mine in the world, and sodium chloride mined in Kura, Pakistan, which is the second largest mine, both consist of 39.3% sodium by mass. So basically we gave you all the mass laws as answer choices here, or choice E would be more than one of these. So let's go through quickly and review the mass laws so we can know what we're looking for here. So choice A is law of conservation of mass, which is simply stated as matter is neither created nor destroyed during a chemical reaction. And I don't think either of the scenario that we're describing here doesn't really follow this mass law at all, because we're not talking about a chemical reaction. We're not talking about any sort of transformation. We're just talking about mining salt. So we're not going to want to probably include that one. And then you have the law of definite composition. So this is the one that deals with chemical substances and the fact that all substances have specific mass ratios of elements. So substances are made up of one or more elements. Typically this refers to compounds that have two or more elements in them, but the key point is that all substances have specific mass ratios of elements. And this one I believe will be certainly applicable to this scenario in this question, because here we're talking about the mass ratio of sodium chloride mined in two different parts of the world, and we're telling you that it's 39.3% sodium by mass. And so anytime you see mass percentages of a compound, and specifically for one compound, then you should automatically think about that mass law, the law of definite composition. So this one's going to be included in our answer. Now we do want to see if more than one of these could be possible, so let's go through these. And then choice C deals with law of multiple proportions. This one is perhaps the most complicated, but the key thing you need for law of multiple proportions to be demonstrated is that you're talking about two or more different compounds. So you're talking about two or more compounds formed from the same elements. And there's more to it than this. But in order for the law of multiple proportions to be even recognized you demonstrate it all, you have to be talking about two or more compounds. Here we're only talking about sodium chloride. We're not talking about two different compounds of sodium chloride. We're just talking about sodium chloride. So law of multiple proportions would not really be applicable either. And then finally, the last one, choice D, Dalton's law. You probably haven't heard of it yet, and that's good because we haven't covered it yet. This is not one of the mass laws. Okay? So it is a law, but not a mass law, and so thus not demonstrated here. Dalton's law, as one later, has to do with gases, so we're not talking about gases here. And so the only answer then that works would be choice B, the law of definite composition. So for definite composition, the key features are you're talking about a single compound, and you're referring something about the mass ratio or mass percentages of elements that are in that compound being a specific amount. Okay, so any question on this one or the mass laws in general? All right, so your first question in your exam will likely be about mass laws, so make sure you know them. Next question deals with counting subatomic particles. So there's a lot of variations on this one, where we'd have you count some combination of neutrons, protons, and electrons in a neutral atom or an ion. And so we want to make sure we know how to do that. So if we have here a 55 Mn3 plus ion, so we have to call what this symbol refers to. So the first thing that we can always get, now we're not asked about it specifically here, but we are going to need it as part of both answers. We're looking for here number of neutrons and number of electrons present. We can use the periodic table always to tell us how many protons it has. So if we give you the atomic symbol, and it's a real element, Mn, which certainly is one, the number of protons we can get from the periodic table just by looking at its atomic number. So if we go to the periodic table, and we pull it up, this is whenever it decides to load. Now we find Mn. It's a transition metal. Hopefully you're a little bit familiar with it. And it's right here, and you can see if you zoom in that the number above Mn is 25. So that number is the atomic number, which tells you how many protons are in the nucleus of manganese. And it doesn't matter which isotope of manganese it is, doesn't matter if it's an ion that's charged, it will always have that same number of protons if it's that element manganese, okay? So we get the number of protons very easily, although as we've said, we're not directly asked for that in this question, but we do need it. So the number of protons is 25 from the periodic table. But then to get number of neutrons and number of electrons, we have to use the other two parts of this symbol. So this one here on the left, which is going to be a whole number and not indicated as negative or positive, that's going to be our mass number, which is going to be the number of protons plus number of neutrons. So if you need the number of neutrons, you need to use the mass number, which will be given for a specific isotope. And then so to do that, we know that the number of neutrons is just going to be the mass number, which is 55, minus the number of protons. So there's going to be 30 neutrons in this. So only the answer choices that have 30 neutrons would be reasonable. And then to find the number of electrons, that's where the charge comes into play. So if this was a neutral element, a neutral atom, it would have the same number of protons and electrons, but the 3 plus up here tells us that it has a net positive 3 charge, which means that the number of electrons is going to be smaller than the number of protons. So if we have 25 protons and a charge of plus 3, that means we have 3 fewer electrons. All right, so again, this minus 3 here came from the fact that it's a plus 3 charge and that we have 3 fewer electrons and protons. So remember that when we form ions, whether they be positive ions or negative ions, all we're doing is either adding or subtracting electrons. We're not changing the number of protons or neutrons to do that. And so to figure out how many less electrons we have, we know that the charge is plus 3, so it's 3 less electrons and protons for a total of 22. So that leaves choice B then as the correct answer, 30 neutrons, 22 electrons. Okay, questions on that problem or the topic of subatomic particles? All right, there's not too many variations on this, but just, we could ask you to work backwards. We could ask you to find the mass number if we gave you the protons and neutrons and so on. So it's, again, a lot of different ways of working these problems, but really all the same topics at play. All right. So number 3 takes us to the first type of numerical question that we would likely have on this exam. And so there's going to be some numerical calculation type problems that deal with the energies, wavelengths, and frequencies of photons. This problem has both, just to sort of demonstrate both concepts, but most likely the questions you would have on the exam, you would just be asked for one of those quantities given the other. But we'll go through both of them here to sort of cover it a little bit more broadly. So in an infrared photon has a wavelength of 1234 nanometers. What are the energy and frequency of the photon? So there are 2 key relationships that we want to know for energy, wavelength, frequency, and so on. So the first one is that the product of wavelength and frequency is equal to the speed of light. This is the first one we covered, which was just one of the basic properties of any electromagnetic wave that has a wavelength and a frequency associated with it and moving at the speed of light. So that's going to be true of the relationship between wavelength and frequency. So if we give you one, you can easily find the other. So here we do want the frequency of the photon. And so if we solve for that nu, it's going to be c divided by lambda. Just rearrange this equation. Now what we have to be careful about here, though, is always with units. And so if we put in c, if we go to the periodic table, that's one of the constants that's listed down here below the periodic table. It's actually the very last one, speed of light c, 2.99792 times 10 to the 8th. I just put it in as 3 times 10 to the 8th, which is perfectly fine, but it's meters per second. So the units there are meters per second, typical SI units for speed or velocity. And so when we solve for the frequency nu here, we're going to have c, which is 3 times 10 to the 8th meters per second, divided by the wavelength. The wavelength then needs to also be in meters for this equation to work. So anytime you're using these two equations, the first one here being the relationship between wavelength and frequency, the second one that we'll get to in a second, you want to make sure that your wavelength is always in meters if that's going to be part of the equation. And so we have to convert the wavelength that we're given into meters. So it's 1234 nanometers. And the very common conversion that we're going to do, converting between meters and nanometers, is that it's going to be, we want nanometers to cancel, so it's going to be 10 to the 9th nanometers per 1 meter. Okay? And so what we get is 1.234 times 10 to the minus 6 meters. All right, so it needs to be in the right units before we can put it into the equation. So once we convert it, we put it up here. 1.234 times 10 to the minus 6 meters is the wavelength. And then when we divide those, that will give us the frequency in hertz directly. So it's going to be 2.43 times 10 to the 14. It'll be inverse seconds, or more commonly known as hertz, Hz. All right, so that's the first part of it. And then the other part is there's an equation for energy of a photon, which is E is equal to h times the frequency, which is equal to hc over lambda. Now for this problem, we could, in practice, use either form of this equation because we were given wavelength directly, but we just spent a step solving for frequency, so we already have the nu if you want to use it. So either of these equations will work just fine in any situation. So here we could either put the lambda directly in, again the same one with the same units, or we could just use h times nu since we already found what nu is. So I'll do it that way, a little bit faster maybe, but it doesn't really matter. So it's going to be 6.626, h is 6.626 times 10 to the minus 34 joules per second, and then multiplying that by the frequency, 2.43 times 10 to the 14 hertz, gives us the energy of a single photon. And it's possible that this step here would have caused a little bit of rounding, but what we get is somewhere around 1.61 times 10 to the minus 19 joules. All right, so that's our frequency, that's our energy, and the answer choice that has those two together is choice A. Keep in mind that for some problems like this, you'd actually have to enter the number in, and most often for large exponential answers like this, especially if we were asking for that frequency of 2.43 times 10 to the 14th, at least the older versions of Blackboard didn't really like exponential answers, so we had a lot of questions still built in there where you have to take the log of the answer. So make sure you know in your calculator how to take the log, because very often you would have to get this number, and then even though there's no real meaningful reason to do this, you would take the log of that answer and then report that in Blackboard just because it's an easier format for Blackboard to accept if we're doing a numerical question. So with calculations like this, it's going to be a combination. Some will still be multiple choice where you just have to pick the answer out of the choices. Others you'll have to type the answer in and just make sure you follow the directions closely in Blackboard. I don't want to see anybody missing the problem because they did it correctly but just didn't follow the directions in Blackboard, okay? So any questions on this one or the topic of photons in general? All right, next one is also dealing with some similar sort of ideas, but here we're talking about the concept which is called photoelectric effect. So for the metal hafnium HF, it is observed that light with wavelength less than 318 nanometers is required to eject an electron from the surface via the photoelectric effect. What is the threshold energy for hafnium in joules? All right, so basically what the way the photoelectric effect works, it's not terribly important for solving this question, but it's helpful to understand the concept for perhaps some other things that'll come up on the test. So in photoelectric effect, you have a metal surface, and as we'll learn later on in the semester, metal surfaces have very loosely held electrons. So what you can do with metal surfaces is you can shine light on them, and if the light has enough energy, it will start ejecting electrons from the surface. All right, now basically though, the energy of the photon, h times the frequency as we just said, has to be greater than some threshold energy, E0. If it's not greater than that, nothing happens. If it is greater than that, then you start ejecting electrons, and depending on what the frequency is, you're going to start ejecting electrons faster and faster and faster as you increase the frequency or energy of your photon. But again, only when you're above the threshold energy and the corresponding frequency and wavelength that correspond to that are you going to actually start ejecting electrons. So this question, what we're saying is that the wavelength that's required to eject an electron must be less than 318 nanometers, and so then it's, what is the threshold energy? So basically the threshold energy, E0, or what's sometimes called the work function, is related to frequency and wavelength just by the photon energy equations, because it's just a photon of light that you're using for photoelectric effect. And so this threshold energy or work function, as it's called, which is what we're solving for here, it's just the energy of the photon, the minimum energy of a photon needed to eject an electron, and that's going to be related to the minimum frequency of the photon or the maximum wavelength, lambda 0. So all these parameters, the threshold wavelength, threshold frequency, threshold energy, they're all just related because it's just a photon, and so you can use the energy for the equation for the energy of a photon to relate those to each other. So what we're looking for here is E0, and we're given the threshold wavelength lambda 0, so we're just going to solve for E0, which is hc over lambda 0. We're going to use that form of the equation since we're given a wavelength directly. We don't have to necessarily do it in 2 steps. And so what we end up with, if just putting the numbers in, is 6.626 times 10 to the minus 34 for h, joule seconds, 3 times 10 to the 8th meters per second for c. All right, and then the wavelength is 318 nanometers. So we once again need to convert that to meters before we put it in, so that in meters is going to be 3.18 times 10 to the minus 7 meters. We have to divide by 10 to the 9th once again. So what we get is 6.25 times 10 to the minus 19 joules. So that would be the minimum energy required to eject an electron. This wavelength, 318 nanometers, is the corresponding wavelength, which would be the maximum wavelength, because energy and wavelength are inversely related. So in order for the energy of the photon to be larger, the wavelength needs to be smaller than whatever that threshold value is. So really it's just the same equation we used in the last problem, just thrown into a slightly different context. So we're not going to do anything in terribly great detail about photoelectric effect, but it is helpful to know the concepts that are involved and how these photon equations are still relevant to those as well. So any questions on this one or the photoelectric effect in general? Yep. So it was given to us in the problem here. So we're saying in the problem that light with wavelength less than 318 nanometers is required, and so that is going to be your threshold wavelength. Yeah. Anything else? Yeah. If the wavelength is more than 318, then nothing happens. That would mean your energy would be smaller than this threshold number, and then the electrons wouldn't be ejected at all. Yep. No. So if you're calculating the energy of a photon, or the wavelength or the frequency, it should always be a positive number. The only time we're going to do the Bohr model here in a second. And so in those you can get a negative delta E. Delta E can be negative for the Bohr equation, but the energy of the photon or the wavelength or frequency of the photon that's associated with that should always be a positive number. Anything else? Okay, so let's go on to, so this takes us now to the Bohr model. we want to know what is the frequency of a photon needed to promote an electron from hydrogen's ground state into the third shell. And then this is another one where we want you to report, in this case, the log of your answer to 2 decimal places. So typical setup in Blackboard that you might see, especially for large exponential numbers. Okay, so anytime you see hydrogen, third shell, ground state, photon energy, photon frequency, those key words, you should automatically think of the Bohr equation here, which is the change in energy or difference in energy between 2 levels in a hydrogen atom given by minus 2.18 times 10 to the minus 18 joules. And then since we're talking about the difference between 2 energy levels, it's going to be 1 over nf squared, where that's the final value of n that you go to, over 1 over ni squared, which is the initial value of n that you start with. So that's typically going to be the first part of any of these questions. Now, most of these problems are going to be at least 2 parts involved. You're going to have to use this equation to figure out, okay, what's the energy change of the electron as it goes between those levels, and then most often you're going to take that energy change and relate it to the energy of the photon that's either absorbed or emitted during that process. Because remember, anytime an electron moves between energy levels in the hydrogen atom, that's going to either be absorbing a photon if it's going to a higher energy level, or it's going to be emitting a photon if it's coming back down to a lower energy level. And the energy of the photon is directly related in magnitude to the change in energy delta E for the electron as it goes through that process. So you're going to typically want to calculate delta E first and then relate it to wavelength or frequency as directed in the problem. So that's what we're going to do here. We're going to use this equation and then the 2 values of n. So we're going into the third shell, so that tells us that nf equals 3. And then from the ground state, so remember, anytime you see ground state, that tells you n equals 1, and so that means our initial value of n is 1. So we're going from 1, which is the ground state, to higher energy 3, so this is an absorption process, and those are the 2 values of n that we're going to want to use. 1 over 3 squared, which is n final, minus 1 over 1 squared, which is n initial. So we get a positive delta E, as we should, because it's an absorption process. We're going to higher value of n. I got 1.94 times 10 to the minus 18 joules. Now, as I said, if this is going to be typically related to the energy of the photon in some way, so the energy of the photon is the absolute value of delta E. Remember, photon energies, as we just clarified, are always positive numbers. So whatever your delta E is, the absolute value of that is the energy of the photon, and that's related to the frequency and the wavelength of the photon in the same way as we've been using for these last couple of problems here. Last 3, I guess. So those are the relationships that are at play here. In this problem, we want the frequency of the photon. So we're going to, basically, the frequency is going to be given by the energy of the photon divided by h, just rearranging this equation here. Okay, and so what we get then, the energy of the photon is just the absolute value of that number, which is just that number, 1.94 times 10 to the minus 18 joules, and then we're going to divide that by Planck's constant h, the same familiar one we've been using. And that gives us 2.928 times 10 to the 15th hertz. And then the log of this answer, which is what we're asking you to report here, is going to be 15.47, reported to 2 decimal places. So again, there's no scientific reason for taking the log. It's just that that's an answer format that Blackboard is easier to accept, at least especially in the olden days when a lot of these questions were first put together. Okay, so any questions on this one, the Bohr model in general? So there's several variations on Bohr model questions, but you've hopefully seen just about all of them by now. There's not an infinite number of variations on these. So it's going to typically involve the Bohr equation to find delta E, but then from there relating it to energy or wavelength of a photon using one of these equations secondarily. All right, questions on that? right, so let's, we've gotten through the first quarter. So let's go to the next one, which is dealing with quantum numbers. So a lot of possible quantum number questions on this test. So I can't cover all the different variations, but this would be a potentially typical one. Which of the following is a valid set of quantum numbers for a 4D orbital, where again the quantum numbers for an orbital are going to be a set of 3, n, l, and m sub l, which these would work for a 4D orbital. So we look at what we're told, which is a 4D orbital. So remember that when we're classifying orbitals or subshells with this number and letter designation, the number tells us the first quantum number n directly. So 4D means n equals 4. That's the easy one to get. All of these have n equals 4, so that doesn't help us eliminate any answer choices. And then the D part tells us the second quantum number L, but it's given as a letter. So if you recall that L can be 0, 1, 2, and 3 if n equals 4. And those are going to correspond to the letters S, P, D, and F. And so if we're talking about a 4D orbital, that means L equals 2. So that means for any 4D orbital, the first two quantum numbers have to be 4 and 2 to be 4D. And then you have to have a valid m sub L as the third number in that series for it to be an actual correct 4D orbital. So what we'll recall is that the allowed values of m sub L, they can range from negative L to plus L, including 0. So if L equals 2, the possible values for m sub L are going to be minus 2, minus 1, 0, 1, and 2. Negative L to positive L and everything in between. And so in order for this to be a valid set of quantum numbers for 4D, m sub L has to be one of these values here. So if we look at the answer choices, choice C is out because it has the wrong L value. Choice E is out because it has the wrong L value. And then between A, B, and D, they both have the first two quantum numbers correct, 4 and 2. But in choice D, this number here, 3, is invalid for m sub L. And similarly for choice D, you cannot have non-integer m sub L values. M sub values are always integer values. So that's wrong, meaning that choice A is the only one that works. 4, 2, minus 2. We did say minus 2 was the minimum value of m sub L, so that one is allowed. All right, so you do need to know the sort of rules and relationships between the three, technically 4 quantum numbers, but these 3 are the ones that are related to each other in different ways, and sort of a little bit about what they mean to be able to identify things like this. Like I said, there's a lot of variations on these types. We'll probably have a couple more, 1 or 2 more in this review that deal with quantum numbers in some capacity, but this would be a typical type of question and gets at a lot of the concepts related to those. So any questions on quantum numbers or this one in particular? All right, so then our next one here is, there's going to be a lot of questions like this where you have how many orbitals are in a given shell or subshell, or how many maximum total electrons, and so on. So it depends on what you're given, what equation you're going to use. So if we're talking about a shell, which means we know just the value of n by itself. Remember that n is the shell number, so if you know the value of n, that tells you what shell you're in. If you're in a given shell, the total number of orbitals in that whole shell is going to be given by n squared. So these are helpful relationships to know, because really the only other way to do this would be to write every, if you're asking for how many orbitals there are, write every allowed combination of n, l, and m sub l, which can get kind of unwieldy if you have an n value that's, let's say, 3 or larger. I mean, for n equals 1, n equals 2, that wouldn't be too terrible, but for anything larger than that, you're going to be writing all kinds of numbers out, and it's easy to miss one or so. So for these, you're going to want to use the relationship. So if you know what shell you're in, the total number of orbitals in the shell is n squared. And then if you're designating a subshell, which means you need to know, in addition or exclusively, the value of L, the number of orbitals is given by (2L plus 1). So in this problem here, we're looking for the number of orbitals in a sublevel where n equals 5 and L equals 4. So if you're given the value of L, you need to use the 2L plus 1 relationship to find out how many orbitals would have that n and L value. Okay? So we're going to put in L equals 4 into this equation. which gives us 9 orbitals. Okay? So that'd be choice D. So you want to make sure you don't use the n squared one, because the n squared relationship would give you 25 if n equals 5. That would tell you that there's 25 total orbitals in the n equals 5 shell, but we're looking for how many have n equals 5 and L equals 4. So of those 25, 9 of them would have L equals 4. Yep.
So if we're given L, we use the equation 2L plus 1?
Yes.
But if we're not given L, then we use n squared.
Yeah, if you just have n, you use n squared. So basically, that n squared equation is how many orbitals are in a shell. If you want to know how many orbitals are in a subshell, which involves the value of L, you would use the 2L plus 1. And so this is a subshell because it's defined by both n and L quantum numbers. So there's 25 total in that shell, but 9 of them would be in that subshell. Okay. Now there's a slight variation on this question as well, which is that we could ask you also in a given shell how many total number of electrons, or the maximum number of electrons, and recall that there's a total of up to 2 electrons per orbital. So if you have n squared orbitals in a shell, that means you have at most 2 n squared electrons. So if we ask you for how many total electrons, or what's the maximum number of electrons, is sort of the best way to ask that. It would be 2n squared for a given shell, and then for a given subshell, again, where you know the value of L, you'd have to know the value of L for it to be a subshell. The maximum number of electrons is just 2 times 2L plus 1. So in the n equals 5, L equals 4, total in n equals 5, you could have up to 50 electrons, 2n squared. But then of those, you'd have a maximum of 18 that have n equals 5, L equals 4, 2 times this number here. All right, so again, make sure you know which equation to use in which situation, depending on whether we're asking you for the number of orbitals in a shell or subshell, or maximum number of electrons in a shell or subshell. They're all related to each other, but you have to make sure you use the correct one. All right, any questions on that? All right, so our next one here is another one that is related to really the same concept. So there's nothing new here. So I kind of jumped the gun in some sense, but we're here, we now just cover what we're doing, so hopefully this one makes more sense now. So we have, what is the maximum number of electrons allowed in the n equals 5 shell, and how many of these can reside in the 5f subshell? All right, so what we're going to do here is, for n equals 5, so we want to know how many maximum electrons are there in the n equals 5 shell. I actually just said that number. The maximum number of electrons is given by 2n squared for a given shell. So if n equals 5, 2 times 5 squared is 50. So that means there's a maximum total of 50 electrons that can be in the n equals 5 shell. The second part of the question is how many of those could go into the 5f subshell. So if you want to know how many go into a subshell, you need to use the value of L that's associated with that subshell. So remember that the L values 0, 1, 2, 3 correspond to the letters S, P, D, F. So we're talking about 5f, that means it's L equals 3. So the maximum number of electrons are going to be 2 times 2L plus 1 for a given subshell. We use the value of L in this case, so it's going to be 2 times 3 plus 1 equals 14. Now remember that these ones for maximum number of electrons in the subshell, we can use the periodic table in some sense to help us for ones that are actually on the periodic table. So if we go to the periodic table, recall that, and we're going to come back to this a little bit later when we do electron configurations, each block on the periodic table, how many columns is that block tells you how many maximum electrons can go in that subshell. So this is the S block, which means all of our S subshells, 1s, 2s, 3s, and so on, can have a maximum of 2 electrons in them. The P subshells, 2p, 3p, and so on, have 1, 2, 3, 4, 5, 6 elements in them, so that means there could be a maximum of 6 electrons in P. The D, which is here in the middle, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, maximum of 10 electrons in any D subshell. And then down here we just did 5F, so any of the F subshells would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, which is the number that I believe we just came up with. Yes, 14. So you can use the periodic table to help you. Now that said, this relationship, 2 times 2L plus 1, could be helpful because we could give you values of L beyond 3, which are not on the periodic table. So if we give you L equals 4, L equals 5, even though those don't exist in atomic ground states, they are still subshells that exist, and that could potentially be populated with electrons. And so if you want to know how many electrons goes into one of those, this relationship 2 times 2L plus 1 is still good to have in your back pocket. So, you know, a lot of this stuff does come from the periodic table, but that's only true if you're going up to L equals 3, because we have up to the F subshells on the periodic table, nothing beyond that. All right, so back to this one, and the correct answer for this would be choice C, 50 electrons total in N equals 5, 14 of those in the 5F subshell. All right, so questions on those concepts? Yeah.
So the number associated like F, so 5 and F is 0.
For calculating the number of electrons in a subshell, the value of N doesn't matter, you're right. So if you're calculating the number of electrons in any F subshell, whether it's 4F, 5F, 6F, 7F, whatever, you would use this same equation, it would still give you 14. So any F subshell. And that's why when you look at the periodic table, as we go, you know, 2p, 3p, 4p, 5p, or 3d, 4d, 5d, as you go down the periodic table, they're still the same width because the number of electrons in a subshell only depends on the L value, not on the N value, which is changing as you go down the periodic table, but the width of the columns and the number of electrons that then correspond to that only depend on the L value. Yep.
Can you explain visually like the difference between a shell and a subshell?
You asked me to visualize quantum mechanics. That's challenging. Okay, so one way to think about it is sort of like classification and subclassification. So when you have N equals 5, that defines a shell. And within that shell, there's going to be, in most cases, unless it's N equals 1, there's going to be more than one subshell below that. Not really below that, but if you want to think about it sort of in a organizational sense, if you have N equals 5, you'd have a total of maximum of 50 electrons. And then if you're putting 50 electrons into N equals 5, some of those are going to go into the 5s. So you're going to have 5s would be 2 electrons maximum. 5p would be 6 electrons. 5d would be 10 electrons. 5f would be 14. And then here's the part that I have to think about. 5g would be 11. Yes. No, so hang on. So it's L equals 4. So that's not, 18. And then 5H, I guess would be L equals, or is that how you can go? I think that's as you can go. So yeah, 5 subshells, 5S, 5P, 5G, 5G, L equals 4, that's 9, 18, right. So this is sort of the distinction between a shell and a subshell, where in N equals 5 you'd have a maximum of 50 electrons. If you're going to put 50 electrons into the N equals 5, this is how they would distribute into the different subshells. They're not all 50 going to be in one subshell, they're going to be distributed in this way. Now what the sort of meaning of it is, the value of N tells you it's related to how far away on average the electrons are from the nucleus. So that part of the Bohr model is still true in quantum mechanics, that the larger the value of N, the further away from the nucleus you tend to be on average. And then it's also related to some extent to the energy. So as you go to larger values of N, the energy of the electrons goes up and up and up. When you're in a specific subshell, you have additional information then about the electrons, because the type of subshell that you're in tells you the shape of the orbitals. So s orbitals being spherical. So the 5s electrons would be in a probability region that's spherical in shape. The 5p electrons would be in probability regions that have more of that figure 8 shape to them. The 5d would have 4-leaf clover shapes. So when you know the subshell within a shell, it gives you some more information about the shapes of the orbitals, and then stuff that we'll start to learn a little bit later on is that the type of orbital that the electron is has an effect on how it can bond with other atoms to make covalent bonds. So there's a lot more to it, but the they're hard topics to visualize because they come from strictly mathematical origins. But basically what you have is that these different quantum numbers, n, l, and m sub l, these are part of the wave equations for electrons. And each quantum number tells you something different about the electrons when it has that specific wave equation. All right, so that was probably an unsatisfying answer, but likely the best I'll do for now. So any other questions? Yeah. Maybe. They're alphabetical after this, so it basically goes S, P, D, F, and then G, H, I, K. They might skip L, but you won't go anything higher than this. So it's pretty much alphabetical after F, so it's not too bad. And I think typically if it's higher than F, we'll give you the L value, but I don't want to say it's 100% true on every question, but the ones that I remember looking at, if it was a larger value of L, the L value of L would be specified. All right, anything else? All right, so now we're getting into electron configurations. So number 9 here asks us about the ground state electron configuration for manganese Mn, which you should know what that is, so I didn't put the symbol here. So this is one of the first 36 elements on the periodic table, manganese, and so you need to know that the symbol is Mn to be able to find it on the periodic table. And then what we're going to do, all of these are given in the shorthand notation with the argon core electrons, so that should be correct, and we'll verify that that's true. So Mn is here number 25. We actually had a problem with it earlier, dealing with subatomic particles. So argon will be the core electrons. Remember, we first find the noble gas that comes before it and abbreviate those core electrons with just the name of the noble gas in brackets. So that's going to be argon for manganese, for Mn. After argon, here we're in the fourth row of the periodic table, 1, 2, 3, 4. So this is going to be 4s, 1, 2. After 4s, it's going to be n minus 1d, so it's going to be 3d. So it's going to be 3d, 1, 2, 3, 4, 5, takes us to manganese. So it's going to be the fifth element in the 3d block, meaning it would end up with a 3d5 valence configuration. So the total configuration is going to be argon, 4s2, 3d5. Now, one thing you should do when you're this one, you don't get helped out by this hint, but it could help you on some of the test questions. When you're picking an electron configuration out of a series of multiple choice answer choices, make sure they have the right number of electrons in them first of all. Okay, so manganese, atomic number 25, should have 25 electrons. If any of these answer choices didn't have 25 electrons in them, they can't be correct. So argon is 18, and then plus 7 is 25. All of these do have 25, so sorry, that little shortcut doesn't help you eliminate anything, but it'd be pretty common in the exam that one or more of your answer choices won't even have the right number of electrons in it, so don't even bother looking at it any more closely than that. So this one must have 25 electrons, all of these do, but now we have to just figure out this is the correct ordering of the subshells, 4s2, 3d5, so choice A is going to be the right one here. In choice B, we went from 4s to 4p, so we skipped 3d, which we can't do. Remember, we always go in order of atomic number. We don't skip any subshells as we're going through the periodic table and building up. This one, remember that this one is wrong because remember that it's n minus 1d, not nd. So it should not be 4d5, it should be 3d5 for that fourth row of the periodic table. And then here we're in the fourth period, so the s electron should be n equals 4, not n equals 3. Okay, so these other three were not too far off, but the only one that has all the subshells indicated correctly with the number of electrons is choice A. All right, remember that for all but two elements, we're going to just use the periodic table to predict the configuration. There are two exceptions we want you to be aware of, and just to remind you of them here. For chromium, which is one before manganese, we take one of the s electrons and bump it up to 3d, so it becomes 4s1, 3d5. We don't fill the s subshell completely before putting in d electrons, And then similarly for copper, we're going to borrow one from the S subshell and bump it up to D as well to become 4s1 3d10. So these are the two that don't quite follow the predictions from the periodic table, so you need to make sure that you know these two exceptions. In reality, there's a lot more than two exceptions, but these are the only two that we want you guys to be familiar with. Anything else, just use the periodic table as I showed you just there to figure out what the predicted configuration would be, and then that's going to be your answer. Okay, any questions on this topic? Let's go on then to number 10, and then this is a related one. Now we could ask you about specific atoms, but in this case we're giving you a partial, or I guess complete electron configuration showing the different subshells. Remember that these are at different energies, even though they're shown horizontally. So 1s would be lowest, then 2s, then 2p, but we're just showing them all horizontally here. But we want to know which of the following reflects an atom in the ground state. So remember that when we're building up ground state electron configurations, there's essentially three rules we have to follow. So one is called the Aufbau principle, and that's what following the periodic table allows us to do. We fill the lowest energy to highest energy subshell in order, and we need to completely fill one subshell before moving on to the next one. Except for those two exceptions that I just told you about in the last one, any other situation you want to make sure that you fill a subshell completely before putting electrons into the next subshell. So that's called the Aufbau principle. You fill the subshells lowest to highest in increasing energy, and you make sure you fill a subshell completely before putting electrons into the next one. So that's the Aufbau principle, so that needs to be true for something to be in its ground state. And then another one that comes into play with degenerate subshells is Hund's rule, where you want to maximize the number of unpaired electrons. And so what this basically says is that if you have two or more orbitals at the same energy, it's going to be either 3 orbitals for a p subshell or 5 orbitals for a d subshell for just atoms. You want to make sure that you have as many unpaired electrons as possible, meaning that you're going to take each orbital and fill it with one electron first, all with the same spin, before you start pairing up a second electron into the same orbitals. That's what Hund's rule deals with. That one doesn't come directly from just following the periodic table and writing out the electron configuration. That one you have to, again, look more closely at the arrangement of the electrons and their spins. And then the last one is Pauli exclusion, which is that no two electrons have the same quantum numbers. And practically speaking, that means you can't put more than 2 electrons into the same orbital, and if you do put 2 electrons in the same orbital, they have to have one spin up, one spin down. So anytime you see, I don't think that comes into play in this question, but if you were to see 2 electrons in the same orbital both spin up, that would violate Pauli exclusion principle because both of those electrons would have exactly the same quantum numbers as each other. So we're going to go through these answer choices and figure out then which of these would follow all of these rules and thus represent a ground state. So choice A here, okay, we filled the 1s, that's good, filled the 2s, that's good. Then we start putting electrons into 2p. What you'll notice is that even though we have individually filled 2 orbitals as we should, one is spin up, one is spin down. Whenever we fill orbitals individually, they should all have the same spin. So this one is going to violate Hund's rule because the second electron has the opposite spin as the first, okay? So they don't necessarily both have to be up. Conventionally, that's how we draw them, but they have to be the same is the key. All right, so in a partially filled degenerate subshell like this, the first 3 electrons should all go in with the same spin into 3 different orbitals. This one here, the second electron has the opposite spin. If we go to choice B, what we'll notice is that we have 1s is filled, but then we have a gap in the 2s. Remember, each 2s orbital can hold 2 electrons, one up, one down. We basically skipped this and started putting electrons into 2p, so this is going to violate the Aufbau principle because we started filling the 2p subshell before we finished filling the 2s, so this violates the Aufbau rule. Okay. If we go to choice C, this one I don't see any problems with. So we fill the 1s, we fill the 2s, and then if we go to the 2p, there's 2 electrons in here. They're in 2 different orbitals and they have the same spin. Those are the key requirements. They don't have to be in 2 orbitals next to each other. They don't necessarily have to both be up or both be down. It's just that they have to be in two different orbitals with the same spin. That is a true arrangement here. So there's a lot of different arrangements that could work for two electrons, but this one does follow all the rules. Two different orbitals, same spins. So this one looks good, so we'll pick that. And then to verify once again that we don't want choice D, this one follows the off-bound principle because we go 1s, then 2s, then 2p, but you'll notice again that we we started pairing electrons right away, whereas we would want to maximize the unpaired. So this is going to again violate Hund's rules. All right. So choice C is the only one that follows all of these three parameters that you need to follow for a ground state electron configuration. So any questions on that one? Yep.
Can you explain Pauli exclusion again?
So Pauli exclusion principle, the simplest way to say it is that no two electrons in the same atom can have the same set of quantum numbers. In reality, when you're looking at diagrams like these, you want to make sure that basically you don't have, so if we had one orbital, you don't want to try to put 3 electrons in the same orbital. So basically the consequences of Pauli exclusion are 2 electrons per orbital. And then also, if you have 2 electrons per orbital, they have to have opposite spin. So this would violate the Pauli exclusion principle because both electrons have the same m sub s value, which means that all 4 of their quantum numbers are the same. So those are probably the 2 things to look for with Pauli exclusion, is that to make sure that each orbital has no more than 2 electrons in it, and if you have 2 electrons in the same orbital, one up, one down. Any other questions? Yeah. There could be questions like that where we ask you which specific rule that it violates. It could be like this, where you just have to pick the one that's correct, or it could be, more specific question of which rule is violated or which of these violates the specific rule. So there's some variations on that. So you want to make sure you have a good working familiarity with all 3 of these principles. Yeah.
So why is D wrong if we know that there should be more facing up?
D is wrong because if you're going to put 2 electrons into a 2p subshell, they need to be in 2 different orbitals with the same spin. So here we put both of them in the same orbital, meaning that we're not maximizing the number of unpaired electrons.
So there wouldn't be one spinning a different direction without the other one still first.
Yes. Yep. Answer choice B is wrong because we did not fill the 2s subshell completely. Notice that this 2s only has 1 electron in it. So you always want to fill a subshell before putting electrons into the next one. So 2p is after 2s, and so you want to make sure that you have both electrons in 2s before you started putting electrons into 2p. So this violates the off-bound principle because we skipped part of the 2s subshell before moving on to 2p. All right, anything else? All right, we're at the halfway point. Let me hydrate real quick, and then we'll get on to the second half. All right, this one here deals with the classification of elements and then also predicting the charges formed by when they make ions, either cations or anions. And so there will be some potential questions about classifications. Again, non-metal and metal being sort of the grossest divide, but you have some other sub-classifications within there. So we have potassium, aluminum, and selenium, so we need to find these on the periodic table. So potassium is atomic symbol K, so it's here number 19. So anything that's on the left side of the periodic table is a metal. Anything in these first 2 columns in particular is called a main group metal, as well as some of the ones over here. So the ones that are in the S or P block are called main group elements. So potassium is a main group metal, and then the predicted charge of the ion would be, anything in the first column is going to form a +1 cation. So remember that when atoms lose or gain electrons, they want to get to the noble gas configuration. So for elements in the first column, the easiest way to do that is just to lose 1 electron to achieve the configuration of the noble gas that comes right before them. So potassium would lose 1 electron to get the argon configuration. All right, so if we look at that answer choice then for potassium, it is a main group metal, that's correct, but it should form a +1 cation, not +2. So the expected charge that we gave you is wrong. That should be +1. So that's that answer is certainly not going to be part of our choice. If we go to aluminum, Al, this is the one that perhaps is one of the least obvious. So aluminum is here, and it's sort of close to that imaginary staircase that divides the metals from the nonmetals, but it is to the left of that staircase. The staircase goes basically above it and to the right of it. And you guys have probably used aluminum foil at home, and is there any question in your mind that aluminum is a metal? I mean, when you think of metal, what do you think about? Shiny, silver, like stuff like that, right? And aluminum foil is definitely a metal. So even though it's not the most obvious place in the periodic table, aluminum is a metal, and it's a main group metal because it's in the P block. Anything in the S or P blocks is considered a main group element. So aluminum is a main group metal, and the expected charge, again, not super obvious for this one, but is one that we want you to know. Aluminum has a valence configuration of 3s2, 3p1, and so it is able to lose all 3 of those valence electrons to get to the neon configuration. So because it's a metal, it tends to lose electrons rather than gain electrons. That's a key property of metals, is they form cations, and by losing electrons. And aluminum does that, losing all 3 of its valence electrons to get to the neon configuration. So the expected charge for an aluminum ion will be +3. So if we go back to that answer choice, aluminum, main group metal, +3 cation expected, those are all correct. All right, and then finally, selenium, Se. We had to find that in the periodic table. That's over here, well to the right of our staircase. So the staircase, again, goes like this. So selenium is clearly to the right of that. And so it's going to be a nonmetal. It's in the main group part of the periodic table. So it would be, technically speaking, a main group nonmetal, although all nonmetals are main group. And then we want to find out the expected charge. So this time, because it's a nonmetal, the expectation is that it would gain electrons to get to the noble gas configuration. And so we see that selenium is 2 away from the nearest noble gas. So it would tend to gain 2 electrons to get to the krypton configuration, thus forming a -2 anion. So if we go to that answer choice, selenium, nonmetal, -2 anion, all of those check out. So that means 2 and 3 are both correct, meaning that the correct answer choice for this problem would be E, both 2 and 3 being correct for both the classification of the element as well as the charge that you'd expect if it was forming an ionic compound. All right, so any questions on how you sort of work through that one and how to either classify elements or predict what charges they would form? Okay. On to number 12. This one deals with 3 concepts. So there's, there's 3 properties of atoms that we want you to be able to predict, relatively speaking, based on their location on the periodic table. There's atomic radius, there's ionization energy, and there's electron affinity. And basically, if you look at the general trends for atomic radius, I'm going to draw the directions that it increases. It's going to increase as you go right to left. So remember that the larger atoms are on the left because they have fewer protons in the nucleus. And then it's going to increase as you go top to bottom. So the base of the radius gets larger right to left, and it gets larger top to bottom. Okay? And then if we go to ionization energy or electron affinity, it's going to be the opposite. So if we're looking for the increasing direction for those, is actually opposite of radius. It's going to increase as we go bottom to top, and it's going to increase in general as we go left to right. Now you should be aware, though, for radius we don't really have to worry about any exceptions. The radius is always going to increase in this direction. Yes? What? How the heck did that happen? Well, so the question that you talk about, which ion or ion has the largest radius, was on last year's review. So did you get yours from Blackboard or from a... Okay, so they probably have last year's. That's okay. I just want to make sure I didn't screw up, but typically, well, I do once in a while, so I want to make sure. Yeah, so ChemGym must have given you last year's review. So that's, as I said, a little different. I think maybe one or two, maybe one other new question, and then a couple that got reordered, so you might have a little bit of challenge following along. But if you want the actual questions, I can send them to you afterwards. It's not a problem if you're not in my section. All right, so so anyway, back to this one. We're looking for trends in radius, ionization energy, electron affinity. As we said, radius doesn't really have any exceptions we have to worry about. I mean, it's not a perfectly smooth trend, but we're not going to have you deal with any of the exceptions to it. But for ionization energy and electron affinity, as we move left to right, there are two places where the trend sort of breaks down a little bit. So in group 2 and group 5, it kind of goes in the opposite way. So group 2, you have abnormally large ionization energy, abnormally small electron affinities, and then group 5, same thing, which means if we're talking about ionization energy, as you go from group 2 to group 3, it decreases, even though it's going left to right. And then similarly, if you go from group 5 to group 6, the ionization energy decreases even though you're going left to right. And then for electron affinities, you go from group 2 to group 3, it'll still increase, but as you go from 1 to 2, the electron affinity actually decreases even though you're going left to right. And as you go from 4 to 5, electron affinity decreases because in groups 2 and 5, you have abnormally low electron affinities. So you have to remember that those are the two places where the trend breaks down. Group 2, which is the second column of the periodic table, group 5, which is the nitrogen column. That's where the electron affinity and ionization energy don't follow the expected pattern of increasing as you go straight left to right. But you have to recall where what some of the things are. So that's going to be important for this question for some of them. So here we're talking about choice A, the atomic radius of oxygen is larger than nitrogen. So if we go to the periodic table and find nitrogen and oxygen is to the right of nitrogen. So remember that the radius is going to decrease as we move left to right. So we would expect oxygen to be smaller than nitrogen or nitrogen to be larger than oxygen, however you want to think about that. So for choice A, it says the atomic radius of oxygen is larger than nitrogen. That one is going to be false. Oxygen should be smaller than nitrogen because it's to the right of it. Then if we go to ionization energy and electron affinity, recall that group 5 here is one of the places where the electron affinity and ionization energy don't follow necessarily the expected pattern. So in group 5, if we're talking about ionization energy, which is choice B, the ionization energy for nitrogen is going to be abnormally large. It has a stable S2p3 valence configuration. It doesn't want to lose any of its electrons. It wants to stay with that same configuration. And so that makes the ionization energy of nitrogen abnormally high, which means as you go from nitrogen to oxygen, even though you're going left to right, the ionization energy will decrease a little bit as you go from nitrogen to oxygen. All right, so nitrogen has a higher ionization energy than oxygen, even though it's to the left. That's one of the places you need to be aware of where that happens. So if we go back to the answer choice, ionization energy of oxygen is larger than nitrogen. That one is also false. It follows the basic trend, but that group 5 is one of the places where it breaks down. And finally, if you talk about electron affinity of the two, so for electron affinity, in this case, there is a break in the trend, but, sorry, I went to the wrong file. For electron affinity, electron affinity is abnormally low for nitrogen. So as you go from carbon to nitrogen, the electron affinity will dip as we go from carbon to nitrogen. It's abnormally small for nitrogen, and then it'll raise back up as we go to oxygen. So in that case, oxygen to the right of nitrogen would still be higher in terms of electron affinity. So nitrogen is lower than carbon, also lower than oxygen, so there's a little bit of a dip. And so what you have then is electron affinity of oxygen larger than nitrogen. That one is going to be true, so choice C is the correct answer here. All right. So what's helpful to think about for ionization energy and electron affinity sometimes are little plots like this, which I've drawn in class before, helpful to remind you of. I don't know. This doesn't like it when I erase too much. So what you'd have is basically, let me save this so I don't lose it. in case it crashes when I try to erase. All right, so that's enough erasing. So what you have for these two is if you have ionization energy and you go group 1, group 2, group 3, group 4, group 5, group 6, group 7, group 8. Well, this is the first column of the periodic table. This is the last column of the periodic table. As we said, it's going to tend to increase as you go across for ionization energy. But then what you'll see is that group 2, as we said, is abnormally high for ionization energy. So it's going to be above the trend. And so you'll get a decrease in ionization energy as you go from group 2 to group 3, even though group 3 is to the right of group 2. And then group 4 will follow the trend. And then group 5 is also abnormally large for ionization energy. So between 5 and 6, you're going to have a decrease in ionization energy as you go left to right. And then group 7 follows the trend more or less. Group 8 has a ginormous ionization energy because it's a noble gas, it doesn't want to lose any electrons, but it's furthest to the right and it's the highest, so it doesn't cause any problems with the trend that you would make any predictions about. So that's ionization energy, and if we do electron affinity, this is again the magnitude of electron affinity, more negative being larger in this case, because electron affinity is usually a negative number. This one also tends to increase left to right, as we said. So as you go from group 1, group 2 has an abnormally low electron affinity, so it's going to lie below the trend, and then you'll increase back up as you go from 2 to 3, and then 4, and then group 5 has an abnormally low electron affinity, so it'll be down here below the trend for the red dots, and then group 6, group 7. Noble gases have basically no electron affinity, so they're basically zero. So because again, noble gases have the stable electron configurations, they don't want to add or lose electrons. So this is kind of how the trends look like in rough form. Again, group 2 and group 5 being the two places where you tend to be off the trend, but in two different directions, whether you're talking about ionization energy or electron affinity. Because in those places, you don't want to lose electrons. That makes the ionization energies larger. It's harder to remove an electron. And you don't want to gain an electron, which makes the electron affinities lower, saying that they don't want to add another electron in.
Where does hydrogen fall?
Well, hydrogen's this would just be for the second row of the periodic table where you have all 8 groups. Hydrogen is pretty low in terms of ionization energy, but not as low as you would think because it is more like a non-metal than a metal. So metals tend to have low ionization energies because they're all the way on the left. So like lithium, sodium, potassium, all those. Hydrogen is not as low as those because it does behave more like a non-metal in some sense, but it's still not super high because it is further to the left, only has 1 proton in the nucleus. All right, any other questions? Yep.
In the question, you said that nitrogen had a low, did it have a low of ionization energy because it was 5?
It has a higher ionization energy. So ionization energy is the blue dots here. So group 5 is higher than group 6. So nitrogen is group 5, oxygen is group 6. And so as you go from group 5 to group 6, your ionization energy tends to decrease, so oxygen should be smaller than nitrogen. All right, I think we can move on. Okay. And this was another question about periodic trends for electron affinity. I think this might be another new question because I don't have it in my old version here. So if people that have the old version, this is another new question. So we want to choose the atom that has the largest, i.e. most exothermic electron affinity. So electron affinity tends to increase again as we go left to right. So if we look at the atoms we're dealing with here, we have nitrogen, oxygen, fluorine, chlorine, bromine. So we said that nitrogen, which is in group 5, has an abnormally low electron affinity, so we wouldn't want to choose that one. Oxygen will be higher than that, but then as we go left to right, we would expect that one of the halogens is going to be the highest in terms of electron affinity. Now, one of the reasons I put this question on here is because there is one exception I didn't cover in class that it's not likely that it's going to come up on your test. I'm not saying all of you are going to see this, but there is at least one test question you might have the fortune of getting where you have to know this. So we would predict based on periodic trends that fluorine has the highest electron affinity because it's it's furthest to the left, it's the highest row of the periodic table. It's not a noble gas, so it's fine to add one more electron to fluorine. But it turns out that chlorine is actually a little bit higher than fluorine. It's kind of counterintuitive. Why would electron affinity increase as we go from fluorine to chlorine? And the reason is that basically remember that when you're talking about electron affinity, you're talking about adding an electron to an atom, and fluorine is really small. So if you want to add an electron to fluorine, you have to shove an electron into a small space where it's around a lot of other electrons, and so there's a lot of electron-electron repulsion when you add another electron to fluorine, so you don't get as much of an energy gain as you do for chlorine, where you're adding an electron, but it's in a more sort of spread out area, so that reduces the electron-electron repulsions of that extra electron. So basically the point is that one thing that's going to be helpful to know, because it's not obvious from just the periodic table, is that the highest electron affinity on the whole periodic table is actually going to be chlorine, not fluorine. Now, to be honest, I'm not a big fan of expecting you guys to know these little exceptions here and there, but there's not too many of them, so don't get too upset about it. And again, I'm on your side this time, but I don't have the power to change the test, unfortunately. So we do want to know this exception, which is that for electron affinity, even though fluorine is the furthest to the right and the top, which is the direction where electron affinity generally increases, chlorine is actually a little bit higher in terms of its electron affinity. So the one that has the large electron affinity on the whole periodic table is chlorine, so that would be the correct answer for this one. Even though based on the periodic trend, we might be tempted to pick fluorine because it's above chlorine, as the electron affinity normally increases as we go from lower to higher periods on the periodic table. All right, so any questions on this one? Yeah.
Is it the same thing for ionization energy?
No, ionization energy is not the same. So fluorine, excepting the noble gases, has the highest ionization energy. The noble gases have extremely high ionization energy. That you should be aware of, because remember, anytime you have that stable noble gas configuration, you don't want to lose or gain more electrons. So noble gases have no electron affinity, it's basically zero. It's not undefined, it's zero. And then they have extremely high ionization energies. So noble gases have much higher ionization energies than anything in group 7, and but they have much lower electron affinity. So when you're talking about electron affinity, it's going to be the halogens, group 7, that are the highest, chlorine being the absolute highest, as we said here. For ionization energy, there's no exceptions between chlorine and fluorine. Fluorine is higher than chlorine. It's above it on the periodic table, and for ionization energy, that would still be true. And that's because in that case, for ionization energy, you're not putting an extra electron in, so you don't have to worry about electron-electron repulsions. In ionization energy, you're pulling an electron off, and in that case, because the electrons in fluorine are closer to the nucleus, they're attracted more strongly and harder to pull off than they are in chlorine. So you have to understand the differences between those two, ionization and electron affinity, you have to think about what's happening in each case. For ionization energy, you're pulling off an electron. For electron affinity, you're adding one, and that's why they behave a little bit differently. All right, any other questions? Yeah.
So like, let's say chlorine is a negative charge.
Yeah.
Do we go, then it would be AR?
That would be its electron configuration, yes. And in that case, then it would have, at that point, once you've added one electron, it would have basically no electron affinity because it's already gotten to the argon configuration. So, but yeah, once you add that electron, it has the argon configuration, it's very stable, doesn't want to add or subtract any electrons from there. All right, anything else? All right, moving on then. I think the rest of these are now all very similar to what I had before. I think I've changed the wording on this one, but it's the same basic question. The bond that has the smallest ionic character among the following. So if you'll recall, remember that percent ionic character, or how high or large, percent ionic character, polarity, dipole moment, these kind of all mean the same things. So if we're asking you questions about bond polarity, they might be worded slightly different, but they all kind of refer to the same idea, which is how polar the bond is. So if we want the smallest ionic character, that's a way of saying the least polar bond. and that means you want the smallest difference in electronegativity between the two atoms. So electronegativity is another atomic property, although it's a property of an atom that's bonded to another one. It's not a property of a single atom in this case. And it follows the same periodic trend as ionization energy and electron affinity. It increases as we go bottom to top, and then it increases as we go left to right. And there's really no exceptions in that trend. So when you're looking for polar or nonpolar bonds, basically the further apart they are in electronegativity, the further apart they are from the bottom left to the top right of the periodic table, that's going to give you a more polar or more ionic bond. And the closer together they are in terms of electronegativity from bottom left to top right, that's going to give you a less polar or more covalent bond. So those are kind of the extremes of the scale. So what we're looking for here is smallest ionic character, meaning we want the least polar bond. And again, what's helpful to do for a lot of these questions is to compare two at a time. So if we do carbon oxygen and carbon chlorine, so one thing that's sort of helpful to recall with electronegativity, we don't want you to learn like all of the values obviously, but having some sort of benchmarks in mind is helpful. So fluorine is the most electronegative atom on the periodic table, that you should know. And then the second most is oxygen. So fluorine and oxygen are the two most electronegative atoms, and then chlorine comes after that. So in most cases, going right to left is a bigger effect than going top to bottom, but so if that means fluorine, which is the furthest from left to right and top to bottom, this is going to be the most electronegative, then oxygen, then chlorine. So it's basically electronegativity of 4, 3.5, 3. So they're all not too different from each other, but there is a ranking there that's helpful to know for these three that are all kind of clustered together. Another helpful benchmark for you is going to be that carbon and iodine have pretty much exactly the same electronegativity. I think to two significant figures, they are the same. So basically carbon, and as you go 1, 2, 3 rows over, electronegativity increases, but then you go 1, 2, 3 rows down, electronegativity decreases. And it turns out, just coincidentally, that carbon and iodine, being related in that way, have the same electronegativity values. So that's sort of a little bit helpful to keep in mind, especially since a lot of the, if you go into organic chemistry especially, you're going to be dealing a lot with bonds involving carbon. So knowing the relative electronegativity of carbon compared to other things is helpful. Carbon is similar to hydrogen, a little bit more electronegative than hydrogen, and then it's less electronegative than nitrogen, oxygen, fluorine, chlorine, and bromine, and the same as iodine. All right, so if we go through these ones, if we compare the first two, which is carbon, oxygen, and carbon, chlorine, in both cases, carbon is the less electronegative atom, so it's going to be the delta plus, and the other atom will have the delta minus partial negative charge. And as we said, oxygen has a larger electronegativity than chlorine, and so that means this bond is going to be more polar, okay? Because you have a larger difference between carbon and oxygen than you do between carbon and chlorine. In both cases, carbon is the smaller of the two, but this one, it's a bigger electronegativity than chlorine, so the difference between these is going to be larger. And you can sort of tell that from the periodic table, carbon and oxygen being 2 over from each other, carbon and chlorine being 3 over and 1 down. So it's not the most obvious arrangement, but it's helpful again to remember that oxygen is a little bit higher than chlorine, just to have that with you when you need it. So that means if we're looking for the least polar bond, we can get rid of carbon and oxygen because it's more polar than carbon chlorine, so it can't be the least polar bond of all of these. And then we're going to compare carbon chlorine to the next one, which is carbon fluorine. And again, carbon is less electronegative than both of these, so it's going to have the partial positive charge. And we already said that fluorine is the most electronegative atom on the periodic table, so the difference between carbon and fluorine is going to be larger than the difference between carbon and chlorine. Carbon is about 2.5, chlorine is about 3, so there's a difference of about 0.5 in electronegativity. Carbon has an electronegativity of 2.5 versus 4 versus fluorine, so the difference between those is much larger. So this bond is, if we're doing it in terms of increasing polarity, CF is more polar than CCl, so that one's going to be out as well. And then finally, if we do carbon chlorine versus silicon chlorine, again, the chlorine is the more electronegative atom in each case. So if we look at carbon chlorine versus silicon chlorine, silicon is below carbon, so it has a lower electronegativity value than carbon. So that means the difference between silicon and chlorine is larger than the difference between carbon and chlorine. So you'd have carbon chlorine and then silicon chlorine being more polar than that because silicon has a smaller electronegativity than carbon, meaning the difference between silicon and chlorine is larger than carbon and chlorine. Again, to put numbers on that, I don't expect you to memorize all the numbers, but we said carbon has an electronegativity of about 2.5, chlorine is 3, so the difference is about 0.5 between those two. Silicon has an electronegativity of 1.8 versus 3 for chlorine, so the difference is larger at 1.2. Remember, the larger the difference in electronegativity, the more polar the bond is. So this is the more polar bond, meaning that it can't be the right choice. So of all the ones we compared it to, carbon chlorine was the least polar, and that's going to be the one we pick. So these questions can be a little bit tricky because you have to look at periodic trends. You're not thinking about just a single periodic trend, but really a difference between two electronegativity values, not just one electronegativity that you need. You actually need to think about both of them and how they are related to each other. But in general, the farther apart they are, bottom left to top right, they're going to be more polar, and the closer together they are in those directions, they're going to be less polar. These ones were not the simplest ones, so that's why I wanted to walk us through them and include this on the review, but generally that's what you want to look for when you're comparing bond polarity. Yep, question? So it's not super obvious from the location of the periodic table because if you look at carbon and oxygen, oxygen is 2 to the right of carbon. So oxygen is definitely more electronegative than carbon. If you look at chlorine, it's 3 to the right and then 1 down. So the question is, between oxygen and chlorine, which are related in a diagonal relationship this way, which one's more electronegative? You can't easily predict that. So that's why it is helpful to remember that oxygen is the second most electronegative atom. I think I would recommend all of you guys to just learn that fluorine is the most electronegative, then oxygen, then chlorine. Having those two sort of ranks in your head will help in a lot of these questions, okay? So knowing that oxygen is more electronegative than chlorine, and both oxygen and chlorine are more electronegative than carbon, that means the difference between carbon and oxygen is larger than the difference between carbon and chlorine. Or in terms of absolute numbers, carbon, as we said, has an electronegativity of 2.5, oxygen would be 3.5, so there's a difference of 1 between carbon and oxygen, whereas chlorine is 3.0, so there's about a difference of 0.5 between carbon and chlorine. Carbon and chlorine have a smaller electronegativity difference, meaning they have less polarity. All right, anything else? Okay. All right, this is actually the question that someone asked about before, so it is here, just in a different order. So which atom or ion has the largest radius? So if you're talking about just atoms, just neutral atoms, you can use the periodic trends for atomic radius that we discussed earlier. But if you're talking about atoms and ions, you have to think about a little bit more than that because the location on the periodic table is not necessarily going to tell you whether an ion is larger or smaller than something else. So the key point here, though, is that what we're comparing here are 2 neutral atoms and 2 anions, and we're looking for the largest of those. Okay, so if we compare an atom to its anion, oxygen to O2 minus, okay? Anytime you add electrons to something, it gets bigger. So if it's O2 minus or anything with a minus charge on it, it's going to get larger compared to the neutral atom. So if we're comparing the radius of these two, O2 minus is definitely larger, so we can get rid of oxygen as a choice. And then if we're comparing Cl to Cl minus, anything that has a negative charge is larger than the neutral atom, so Cl minus is definitely larger than Cl. So if our goal is to find the largest one overall, we can get rid of the neutrals because we're not, we know that the neutral atoms are going to be smaller than their respective anions. So really the question comes down to which of these anions is larger, because O2 minus is certainly larger than oxygen, Cl minus is certainly larger than Cl, and for that you want to look at, to some extent, the electron configuration. So for O2 minus, if we go to the periodic table, oxygen with a 2 minus charge has the same electron configuration as neon. So it has 10 electrons, and they're in the outermost electrons are in the 2p subshell. And then Cl minus has the same electron configuration as argon, so it's going to have its outermost electrons in a 3p subshell. All right, so the configuration for O2 minus is going to be neon, and the configuration for CO minus is going to be argon. And again, what that means is that your outermost, your valence electrons are going to be 2p for O2 minus versus 3p for CO minus. And anytime you're comparing atoms or ions and they're in two totally different subshells, remember that the higher the number of the subshell, the higher the n value, on average, the further away the electrons get from the nucleus. So if you're comparing 2p versus 3p, you would always want to assume that the 3p one is going to be larger, okay? So in this case, because it's a 3p versus a 2p outer configuration, we would expect that CO minus is much larger, okay? And so that means CO minus should be the largest overall because we're comparing, again, something that has electrons in its 3p. And so typically going to a whole additional subshell, going from 2p to 3p, that's a very big effect on radius. So obviously these have two different charges. So, you know, well, this one's 2 minus, this one's 1 minus. How does that affect things? It will affect things to some extent, but going from 2p to 3p is a much bigger effect. Going all the way from a 2p subshell to a 3p causes electrons to get much further away from the nucleus. So some of the key concepts here were that anions are much larger than neutral atoms is a huge effect. And when you're comparing anions in the same row, which we didn't have to do here, but if you were, look for the higher charge. The more negative charge, the larger it will be if they're in the same row of the periodic table. If they're in different rows, if it's lower on the periodic table, in other words, a higher period number, that's going to be larger, and that's what we had to deal with here. Okay, so oxygen and chlorine are in two different rows in the periodic table, which means that the valence electrons in oxygen are in 2p, the valence electrons in chlorine, Cl minus, are in 3p. These we would expect to be much further away from the nucleus, so that's why we chose it. So there's some different comparisons that go into play depending on whether the anions are in the same row of the periodic table or not. So if we were comparing O2 minus to F minus, where we have two anions on the same row with the same configuration, O2 minus, F minus, in that case, the one that has a larger charge, O2 minus, would be the larger anion because they're in the same row and they both have 2p electrons. But in this case, oxygen and chlorine are in two different rows, so the primary driver is going to be which subshell the electrons are in. Okay? Any questions on that topic? All right, we're getting towards the end. So this question asks us to predict the formula of the compound that forms when calcium and chlorine react. So for questions like this, what you're essentially doing is you're going to look at the elements that are involved, calcium and chlorine. You're going to predict the charge on each ion that they would form, and then you're going to go from there to get the formula. So it's not too bad to do this. It's worded in sort of a weird way. Well, calcium and chlorine react. What's the formula of the compound? How do we know that? But remember that anytime a metal and a nonmetal react, so if we go to the periodic table, calcium is a metal, it's over here. Chlorine's a nonmetal, it's over here. Anytime you combine a metal with a nonmetal, you're going to form an ionic compound. And when you form an ionic compound, you just need to figure out what are the charges of the ions. That'll tell you the ratio that they combine in. So calcium is the metal in this case. It's in group 2A, so as we talked about a little bit earlier, that's going to tend to then form a +2 cation, anything that's in this second column. And then chlorine over here in group 7A would tend to gain 1 electron to form a -1 anion. So when calcium and chlorine combine, because there's one metal with one nonmetal, they're going to form ions. Calcium would form +2, chlorine would form -1, and then we just have to figure out the ratio that balances the charge. Okay, so calcium, group 2A metal, forms a +2 charge. Chlorine, a group 7A nonmetal, we would predict forms a -1 charge. And so that means when these two elements react, we're going to form calcium 2 plus and Cl minus. And then we just have to figure out the ratio of those two in the balanced ionic formula by just crossing the charges over to make them subscripts, or just making sure we have the right number of each to balance charge, and we get CaCl2. 2 Cl minuses for every calcium 2 plus to balance the charge. That would be the correct formula, which corresponds to choice A. Okay? So really, any question on the test that's worded like this would be of the same type. The only time we can really predict the formula of the compound that forms is if it's an ionic compound. So if it's one metal with one non-metal, they're going to form positive ions from the metal, negative ions from the non-metal, and they're going to combine in the ratio that balances the charge, and that's what you would get. So really, this is just a matter of predicting ionic formulas, knowing the charges of each of the ions that are involved. All right, any questions on that? All right. Number 17, in the Lewis structure for carbon monoxide, what is the formal charge on the oxygen atom? So this is carbon monoxide, which is CO. So we have to know name to formula, or formula to name. So 1 carbon monoxide, CO. It looks pretty simple. Oh, this is a Lewis structure with 2 atoms. How hard could it be? This is actually a little bit more challenging of one than it initially presents as, but nonetheless, we're going to go through it and we're going to make sure that we follow the octet rule for both of these atoms, because carbon and oxygen are both in the 2p part of the periodic table, so they want to have exactly 8 electrons in any Lewis structure. And then once we complete the octet rule, we'll calculate the formal charge for the carbon atom and see what it is. All right, so we have to start by counting electrons to get a good Lewis structure. So we have carbon and oxygen. Carbon is in group 4, so it's going to contribute 4 valence electrons. Oxygen is in group 6, so it's going to contribute 6 valence electrons. All right, so we have 1 times 4 for carbon, 1 times 6 for oxygen, so a total of 10 electrons. All right, so we have 10 electrons in the formula. So now when we go through, and if we want to follow the rules that I sort of gave in class, or the approach that I have for it, we start with single bonds. So we start with the CO single bond. This is sort of, again, the less thoughtful way of doing it, perhaps, but it works. And then what we're going to do is we're going to complete the octet of the outer atoms first. Now the question is, oh shoot, it's 2 atoms. Which one's the central atom? Which one's the outer atom? In reality, it doesn't matter. You can complete the octet of either one first. But by convention, we do the most electronegative atom first, but it wouldn't matter if you did the other way around. So don't think that matters in this case. Oxygen is more electronegative than carbon, so I'm going to complete its octet first, but they should both have a complete octet when we're all said and done. So we're going to put 6 more electrons on oxygen to give it a complete octet. So that's 8 electrons so far, 2 from the bond, and then 6 more as lone pairs, which means we have 2 more left to put on carbon, okay? So what you'll notice right now is that this carbon atom here only has 4 valence electrons. All right, it has 2 from the bond and 2 as a lone pair. That's obviously not good because carbon wants to have 8 electrons. It wants to be a complete octet in all of its Lewis structures. So how are we going to deal with that in this case here? What are we going to do to fix that? We're going to make a double bond. We'll get us partway there, and then take it one step further, triple bond. We basically need to make 2 more bonds between oxygen and carbon to make sure that this has 8 total electrons. So we're going to take off 2 of the lone pairs from oxygen and turn them into a double bond between, or another bond between carbon and oxygen for a total of triple bond. So what we come up with then is a structure that has a carbon-oxygen triple bond, and then 1 lone pair on each. So we can't just add in 2 new bonds. We have to make sure we still keep 10 total valence electrons. So what we did was we took these 2 and made another bond. We took these 2 and made another bond. That's still a total of 2, 4, 6, 8, 10 electrons. But now each atom has exactly 8. 6 from the bond, plus 2 more as non-bonding pair, 1 on each atom. So this is what the Lewis structure for CO looks like. And then what the question was asking for was the formal charge of, in this case, the carbon atom, I believe. No, sorry, oxygen atom, okay? So if we look at the formal charge of oxygen, remember that the way that we do formal charge is we start with the number of valence electrons that the atom has, which is 6 for oxygen. We subtract from that the number of bonds that the atom has. This oxygen has 3 bonds. A triple bond counts as 3 bonds. And then we subtract from that the number of non-bonding electrons, which is 2 for oxygen. This 1 lone pair here. So we get a +1 formal charge for oxygen. And then to make sure there's no problems, we can calculate it for carbon, even though we're not required to here. And for carbon, the formal charge, there's 4 valence electrons for carbon. It also has 3 bonds, so we subtract 3, and then it also has 2 non-bonding electrons, so we subtract 2, we get a -1 for carbon. Now this might strike you as a little bit alarming because in this Lewis structure here, the more electronegative atom, which is oxygen, has the positive formal charge, and that's usually not good. But with this, you can go ahead and try. I won't stop you from trying, but you won't get there. This is really the only way to write this Lewis structure that follows the octet rule. Remember, the octet rule is much more important than anything with formal charges. So even though this is a weird formal charge arrangement, +1 on the more electronegative atom, -1 on the less electronegative atom, that's not usually what you see, but that's the only way we can arrange the electrons to complete the octet. There's no other way to do it. If you try to just do a double bond between the two, one of them is going to have an incomplete octet. There's no way of doing it otherwise. So +1 is the correct value, the correct answer for the formal charge on oxygen. And sorry, hopefully it strikes you as a little bit weird, but it is correct in this case. Carbon dioxide is a weird structure, even though it looks very simple in terms of its formula. All right, any questions on that? All right, home stretch, 3 more. Yep.
In Blackboard, would we just put 1, or do we have to put +1?
It would, in Blackboard, it would specify the format of the answer. Probably for that type of question, it would be multiple choice most likely, but it'll always specify, and if it doesn't, then I won't count it wrong if it does for some reason. All right, this one is nomenclature of ionic compounds, which the following name formula pairs is looking for the incorrect one. I think this might be another new question that I don't have in my old version if you're trying to follow along with the old version. All right. So the first one is strontium 2 carbonate, SrCO3. So if we go to the periodic table and find strontium Sr, it's a main group metal, it's in group 2. And what you'll remember is that for these metals in the first 2 columns of the periodic table, group 1 and group 2, we don't include any Roman numerals in the names of their compounds. Remember, we're only going to use the Roman numerals for transition metals or p-block metals, some of the ones over here, like lead and tin and so on. But for these first 2 columns, you never have Roman numerals, so that's going to be, we think, incorrect, because in strontium, you should not have any sort of Roman numeral. It should just be strontium carbonate. So anytime it's in the first 2 columns of the periodic table, you just put the name of the metal, you don't modify it at all when you're naming an ionic compound. So that, I believe, is going to be the correct answer, A. Let's check the rest of them to make sure. So if we have cobalt 2 nitride, CO3N2, first of all, we will see that cobalt is a transition metal. It's in the middle of the periodic table here. So that means we should have a charge indicated in parentheses for any compound with cobalt. Anytime it's a transition metal, we do that. Let's make sure it's given correctly. So the formula here, CO3N2, remember that nitrogen forms 3- anions. So we have 2 3 minuses, which means to balance the charge, we have 2 3- anions, and that means to balance the charge, we would need 3 2+ cations. If there's 3 in the formula, they each have to be +2. So that's given as cobalt 2, so that looks like it's correct. So here I assume the formula is correct and just check to make sure the name was. So if the formula is correct, CO3N2, that means we would have 2 3- anions, 3 2+ cations to balance the charge, and that means we need to have a 2 in parentheses indicating that the metal has a charge of +2. If we go to calcium phosphate, calcium is another one in group 2A, so it's going to form a +2 cation. And then phosphate here, remember that the charge for phosphate is 3-. So if you have 2 3 minuses, that's a total of 6 negative charges again, which means you have to have 3 of your +2 cations. So this is the correct formula for calcium phosphate and the correct way to name it without any numbers in parentheses. Zinc sulfide. This one's a little bit of a weird one. So zinc is here in the transition metal series, and we're not going to really hold you to this on the test, so don't get too bent out of shape about this, but zinc only forms +2 cations. So you don't have to, and it is in the table in your book, it's there, but it's not going to be a huge point of emphasis. But nonetheless, because zinc only forms +2 cations, you don't have to indicate what its charge is in any ionic formula. So for zinc, you would just put it as zinc and assume that it's +2. So zinc sulfide, S forms a 2- anion, zinc forms a 2+ cation. So the correct formula for that would be ZnS, and the correct way to name it would be zinc sulfide. Okay? And then finally, potassium chlorite. Potassium is K, that's correct, and it's going to be +1. And then chlorite, remember, is ClO2-. So you have hypochlorite, which is ClO-, chlorite, which is ClO2-, chlorate, which is ClO3-, perchlorate, which is ClO4-. So that's probably the most challenging series of those polyatomic anions. All 4 of those just differing with the number of oxygens attached to chlorine. But chlorite, the correct formula is ClO2 with a 1- charge, so that gives you the correct formula with potassium as well as the correct name. All right, any questions on nomenclature? I think our last one might deal with nomenclature too, but no, it doesn't. So that's our only question on nomenclature on this practice exam. So if there's anything else you want me to cover, please let me know. All right, this one here is one of the only types of numerical questions we had from Chapter 3. So Chapter 3 is all about bonding, Lewis structures, nomenclature, covalent bonding, electronegativity, all that stuff. But the only type of numerical question we had was using bond energies to predict the change in energy for a reaction. Now, as I said when I introduced this in class, in my opinion, we're jumping the gun a little bit here and giving you this topic a little bit earlier than we should. But nonetheless, it's not too difficult mathematically, and I think we can handle it at this point. Now, the key though for this type of problem is to make sure that we have the correct bond orders involved, because as we see down here in this problem, we give you carbon-oxygen triple bond, carbon-oxygen double bond, carbon-oxygen single bond, all with 3 different bond energies. You have to make sure you're using the correct number for those. In other cases like CCl, OH, HCl, we just give you 1 bond energy because those pairs of atoms only form single bonds, so you don't have to worry about the bond order. But for carbon and oxygen, you have 3 possible bond orders. You have to make sure we're getting it correct. So you do need to be able to, in some, where they're not usually going to be very complicated, and some of the problems you won't have to do it at all, but you might need to sketch some quick Lewis structures of the reactants and products to make sure you have at least the bond order correct. So I'm going to go through at the very end of this today. I have one extra slide that I'll cover this a little bit more detail, but a little bit of a shortcut to help you with some of these Lewis structures. So if you have carbon in a Lewis structure, COCl2, typically the central atom listed first in the formula, as we said. If you want to sort of quickly get the bond orders correct, a helpful shortcut is that in carbon monoxide being a rare exception actually, but in 99.9% of Lewis structures, carbon has exactly 4 bonds and no lone pairs. And so what that means is if you have COCl2, we need to have 1 more bond to carbon somewhere. And so the logical place to put it is with oxygen, because oxygen, another shortcut that I'll cover a little bit more detail at the very end of this, tends to have 2 bonds. So you want 4 bonds to carbon, 2 bonds to oxygen. This is the best way to do it. You could draw this Lewis structure from scratch using the approach that I follow, but this is a way to save you some time on a longer problem like this. We have COCl2, we have H2O, which is just oxygen hydrogen single bonds. And then what we're forming is CO2. Now hopefully we're familiar with the Lewis structure of CO2 by now. We've done it a couple times. I don't know if I have or not, but hopefully you have on your own. It's 2 carbon oxygen single bonds. And again, following the shortcut. Carbon wants to have 4 total bonds. It's bonded to 2 oxygen atoms, so it's going to have double bonds to each. Each oxygen wants to have 2 bonds, so it's going to have a double bond to carbon. And so that's CO2, and then you have 2 HCl's, which are just hydrogen and chlorine bonded to each other. So that allows us to picture the bonds a little bit better and make sure that we're using the correct bond order. So it turns out the only carbon-oxygen bond we actually need is the double bond. None of these have CO triple bonds. In fact, carbon monoxide is really the only thing that has a CO triple bond in the world. And then none of these species have CO single bonds, even though that is fairly common overall. So then to answer the question that's at hand here, we remember what we're going to do is we're going to sum up all the bond energies from the reactants, we're going to sum up all the bond energies from the products, and then we're going to subtract the 2. So on the reactant side, we have, in our first reactant, we have a CO double bond. So that's going to be 1 of those times 745. So 1 times 745 kilojoules. We have 2 carbon-chlorine single bonds. You have to count each of these bonds individually. So we're breaking all the bonds on the reactant side first. So it's going to be 2 carbon-chlorine bonds. And the correct number for carbon chlorine is going to be this one here, 339. So we're going to do 2 times 339 kilojoules to get the contribution from those 2 carbon chlorine bonds. And then finally, our water molecule that's on the reactant side has 2 OH bonds. All right, so it's going to be 2 times OH. And the OH bond strength is given here as 467. So we're going to sum all of those. I wrote that wrong, my bad. I jumped the gun. That's 934. I thought that looked weird. And then we're going to sum all of these up to get the total of the reactant bond strength, which is 2357. That's that number is. All right, so that's going to be the sum of the bond strengths for the reactants. Then we're going to do the same thing for the products. So these questions are a little bit tedious, so I actually recommend saving them for the end because they're still just worth 1 point. So if you have a question like this, it's going to be towards the end of your exam anyway, but don't fall into the trap of spending 10 minutes trying to solve one question when they're all worth 1 point. So make sure you get through as many of them as possible. But these ones aren't so bad, so hopefully with enough practice you can get through them. On the product side, we have CO2, which has 2 carbon-oxygen double bonds. So we have 2 times 745 for CO2. And then we have 2 HCl's. And HCl is 427. $854. Meaning that the sum on the product side is going to be 2,344, not too different than the reactant side. And then finally, to get the delta E, it's going to be the sum of the reactants minus products. So sum of the bond energies for the reactants, which we did first. And we're putting energy into the reactants to break all the bonds, and then we're going to subtract from that the sum of the bond energies of the products because we're going to release that energy when we form the bonds in the products. And the difference between those is the delta E for the reaction. So 2357 kilojoules for the reactants minus 2344 kilojoules for the products. And so what we get is plus 13 kilojoules. And this just asks you to enter your answer with 1 decimal place and no units. So I guess you would enter it as 13.0, although the 0.0 is not going to make a difference if you forget that. But I'm just following the instructions that I gave here for this hypothetical Blackboard question. All right, but again, it's reactants minus products. So it's more like accounting than chemistry, just adding up a bunch of bond energies. But for this one, it did help to have Lewis structures sketched out first to make sure we're using the correct bond order and the correct number of each bond for the reactants and products, especially the ones that involve carbon, where we had a carbon-oxygen bond that could have been in principle single, double, or triple. All right, any questions? All right, last actual problem on the review. So this is another one with Lewis structures, and we want to draw the Lewis structure of Cl2SeO that minimizes formal charges, and then we want to know how many double bonds are there and how many lone pairs are on the central atom respectively. So this is a typical type of Lewis structure question where, first of all, we're going to specify in many cases what to do with formal charges. If we don't specify, assume that it either doesn't matter or that it's octet, just follow the octet rule. But here we want to specifically minimize formal charges, and then once we do that, we want to know how many double bonds and lone pairs are there, or something about the structure. Because obviously we're not going to have you draw structures on your own in Blackboard. So this is, we did Lewis structures a little bit earlier, but let's do one more. So we have Cl2SO, we have Cl, selenium, and oxygen. Chlorine is in group 7. So we have 2 chlorines, each contributing 7 valence electrons. We have 1 selenium, which is from group 6. It's right below sulfur and oxygen, so it's going to be 6 valence electrons. And then 1 oxygen, which is also in group 6, another 6 electrons. So what we get for this is 26 valence electrons. And then if we're going to draw the Lewis structure, what we start with are the least electronegative atom at the center, which is selenium. This is one where I probably should have specified that selenium is the central atom, but hopefully it makes sense that that's the case. And we're going to start with single bonds to each one. And then we're going to complete the octet of the 3 outer atoms. So we're going to add 6 more non-bonding electrons to each outer atom. So that we've completed now 3 octets, 1 for each of the outer atoms. That's 24 electrons. Still 2 more out of our 26 that are left. That means they go on the central atom. So this structure will have 1 lone pair on the central atom. So that part of the question we can already answer, but we have to evaluate formal charges to know whether we should stop here. Right now, all the atoms follow the octet rule. They all have exactly 8 electrons around them, including the central atom. So we don't necessarily have to do anything else to follow the octet rule, but in this case, we want to minimize formal charges, so we need to check formal charges. And if we check the formal charges for selenium and oxygen right now, we'll do oxygen first. Oxygen was in group 6, so it started with 6 valence electrons. In this current structure, it has 1 bond and a total of 6 non-bonding electrons around it. So remember, a common pattern that we'll see is that oxygen with a single bond has a -1 formal charge. If it's a single bonded oxygen, nothing else, it's going to have -1 formal charge. And then if we go to selenium at the center here, selenium is also in group 6. In this current structure, it has 3 bonds, 3 single bonds, 1 to each outer atom. And then it has a total of 2 non-bonding electrons, 1 lone pair on the selenium that we're going to subtract from that total. So this gives us a +1 formal charge. We are instructed in this problem to minimize formal charges. So what do we do in the situation where we have a +1 and a -1 next to each other? How do we get rid of can we get rid of those or not? All right, so if we want to minimize formal charges, ideally we should have 0 in a neutral molecule. Not always going to be possible, but one way that you can think about doing that is if you have a positive and negative next to each other, we draw a double bond between them. This will require us to expand the octet, but for selenium that's okay because it's beyond the second row of the periodic table, okay? So we're going to take 1 lone pair off of oxygen and turn it into a double bond. And anytime you do that, you take a lone pair from the negative formal charge and then draw it as a double bond to the one that has a positive formal charge. That will cancel out the plus and minus formal charges. And to verify that's true, if we recalculate these formal charges, oxygen in this new structure has 2 bonds and now only 4 non-bonding electrons. So its new formal charge is 0. And then the selenium now has a total of 4 bonds, 2 singles and a double, so a total of 4 bonds. Still has the 2 non-bonding electrons. We didn't do anything to selenium's lone pair, and this now comes out to 0 as well. So if we specify that you want to minimize formal charges, you should look for ways of doing that. And when you have a positive and negative formal charge next to each other, you can achieve that by drawing a double bond, an additional bond between them, making sure that you're not doing anything weird with the octet rule. But in this case, we only had to expand the octet of selenium, which is fine because it's the central atom and it's beyond the second row of the periodic table. So now to answer the question then, how many double bonds are there and how many lone pairs in the central atom? There's 1 double bond and 1 lone pair in the central atom, so B would be the correct answer. Okay, any questions on that? All right, the last thing I want to cover, if you'll bear with me for 5 more minutes, is something that I didn't go through in class but probably should have, which would be completing more complex Lewis structures. So there's going to be not too many on this test, but maybe a couple questions sprinkled into the test bank, but you'll see more of these on chapter 4, so if we can do it now, it'll be helpful. Where we give you a partial Lewis structure and we ask you to fill it in, and then we ask you some question about it. For this chapter, it would be like how many double bonds and lone pairs and things like that. Once you've completed the Lewis structure, in chapter 4, we'll ask questions about the bonding and things that are involved that we haven't got to yet. But we have these more complex Lewis structures, and there's some shortcuts that are going to allow us to complete them quickly. So we'll give you something like this, where we'll draw, it's called a skeleton structure, which just has single bonds between all the atoms. This is a totally hypothetical one, but it'll illustrate all the concepts. So we give you this, and we say, okay, finish the Lewis structure. and then tell me how many double bonds or triple bonds or lone pairs or whatever it has. Now we could follow the rules that I give you, which is, count all the valence electrons and complete octets and evaluate formal charges. But for a structure like this, that takes a long time because there's a lot of atoms that you have to worry about. So that's where there's going to be some shortcuts that are helpful for you to keep in mind. So these types of structures are typically going to have, well, let's start with hydrogen. Hydrogen, carbon, nitrogen, and oxygen are going to be the most common atoms in there. Or maybe X, which is like chlorine or fluorine if it's one of the outer atoms. Not as common, but you can see those. Okay, so these are called organic compounds. You guys take organic chemistry, you'll see these kinds of things all the time. And these are the main elements that make them up. And so when you're completing a Lewis structure, first of all, the one that should be obvious is that hydrogen has one bond. Okay, so in these skeleton structures, they're always going to all have one bond, so you don't do anything to hydrogen. You just leave it as single bonded. Remember that hydrogen never has anything but one single bond. And then to complete their octets and minimize formal charges, these four elements are going to behave in slightly different ways. They're all going to have complete octets, but they're going to do it with different combinations of bonding and non-bonding electrons. So in the vast majority of cases, carbon is going to have 4 bonds and 0 lone pairs. Nitrogen is going to have 3 bonds and 1 lone pair. Total of 8, but different combination to minimize formal charge. Oxygen will tend to have 2 of each, 2 bonds and 2 lone pairs. And then if you have a halogen in your structure, chlorine or fluorine particularly, those tend to have just a single bond and then 3 lone pairs to complete the octet. So all of these P block elements, carbon, nitrogen, oxygen, and then if you have halogens, they want to have complete octets in their structures, but they're going to do that with different combinations of bonding and non-bonding electrons. And if you follow these patterns, you can quickly fill things in and not have to spend forever trying to complete the structure. So if we look at this one here, this carbon right now already has 4 bonds, so it's not going to get any more. It already has a complete octet with 4 bonds. We're not going to add any lone pairs. We're not going to add any more bonds. But if we look at these next 2 carbons here, each of them only has 3 bonds. 1 bond to the carbon before it, a bond between them, and then 1 bond to each hydrogen. So how can we fix this to make sure that these 2 carbon atoms have 4 bonds? Anybody have an idea? I think I might have heard someone say it. Yeah?
Double bond?
Yep, double bond, exactly. So we're going to draw a double bond between those, and that's going to now make sure that each carbon atom has 4 bonds. So typically you can just work left to right in these structures. You can do right to left as well, which should be fine. But in this case, we'll go, we don't want to add any more bonds this way because this carbon's already happy, but then by drawing a double bond between these 2, they both have 4 bonds. If we go to this carbon here, it also has 3 bonds and is bonded to an oxygen that has 1 bond. Carbon wants to have 4 bonds, oxygen wants to have 2 bonds, so the dead giveaway here is to draw a double bond between carbon and oxygen. That will give carbon its 4th bond, that will give oxygen the 2 bonds that it wants. Oxygen should also have then the 2 lone pairs, if you want to, which you should draw in, especially if you're asked about non-bonding electrons. And then finally, this last one here, this carbon only has 2 bonds. It wants to have 4. We can't do anything to this carbon because we've already just completed its octet. But this carbon is bonded to a nitrogen atom that only has 1 bond. Carbon wants 4 bonds, so it needs 2 more. Nitrogen wants 3 bonds, so it needs 2 more. So what you should think about doing is making a triple bond so that each of them have the correct number of bonds. This carbon now has a total of 4 bonds. This nitrogen now has a total of 3 bonds, and then we add the lone pair to complete its octet. So if you follow these patterns for the valence electrons in these more complicated structures, if we give you, the skeleton structure that puts the atoms in the right order and draws in the single bonds, filling in the rest of the structure should not take too long, should not be too difficult if you just follow these few rules here. So if you haven't seen any questions like that on the homework assignment, you will this week, so you'll hopefully be able to use this and practice on it a little bit before the exam. There's not too many questions on this exam that require you to do this, but it is going to be something that continues in Chapter 4 to talk about some other things related to covalent bonding. All right, if there's any last questions, I can stick around, but I'll close this out for now and see you guys next week.